So if the relation on set S is reflexive, antisymmetric, and transitive, then you get something like this, which is basically your set S is being partitioned. Every connected component constitute one partition, and in a partition or in a connected component there is an order, and that order you can show it by the Hasse diagram representation. So Hasse diagram representation of this is 5 and then 2. Why I'm giving 2 and not 1? It's because from 2 you can get to 1, and then 5 to 1 is a transitive edge. We don't draw the transitive edge and the reflexive edge in the Hasse diagram. So from if you look at 2, there is only one incoming edge which is from 5, and that's why you are giving this. And if you look at 1, there is only one incoming edge which is from 2, and that's why that is here. If you look at 3, there is two incoming edge from 1 and from 2, but we will not give this edge in your Hasse diagram because this is the transitive edge. So we will only have from 1 to 3, and then 3 to 4. And let's say this is also connected in this manner. Then there is another. So there is two connected components. There is two connected components, and then 6 to 7. Anyways, so what are the partitions? The partitions are, I can write the partitions of your partial. So this relation R, let's say this is the relation R. Then this R is partial order relation. This R is partial order relation because it is reflexive and antisymmetric and transitive. And in a partial order relation, for every component you have an order. The order is this: 5, 2, 1, 3, and 4. Now, when do you say that X is related to Y from a Hasse diagram? It's very easy. If you have an upward edge, so 5 is related to 2, 5 is related to 1, 5 is related to 3, 5 is related to 4, right? 5 is related to 2, 5 is related to 1, 5 is related to 3, 5 is related to 4. Similarly, 2 is related to 1, 2 is related to 3, 2 is related to 4. 1 is related to 3, 1 is related to 4. 6 is related to 7. So if there is an upward edge from X to Y, then X is related to Y. Or if an ordered pair X and Y is given, and it's a set membership problem, kind of, you can say that whether X comma Y belongs to R or not. This is what you have to find it out. Then from the Hasse diagram, you just have to see if there is an upward edge from X to Y. If there is an upward edge from X to Y, means that X is related to Y. Anyways, we will again get back to partial order relation, post set, lattice, and other things. Right now, in this video, we will talk about what is the equivalence relation. Now, what is the equivalence relation? Relation that is reflexive, symmetric, and transitive. So, partial order relation is reflexive, antisymmetric, and transitive. An equivalence relation is reflexive, symmetric, and transitive. Now, what happens if this is, let's say, let's make this a equivalence relation and see what changes. Now, to make this as a equivalence between any two different nodes, if there is an edge between any two different nodes, it must be a bidirectional node because we want a symmetric relation. Right now, there is only a unidirected edge from 5 to 2. So here 5 is related to 2, but 2 is not related to 5. I want it both ways, so I am going to make it bidirectional. So we make it a bidirectional. You have to make this as bidirectional. You have to make every edge between two different nodes as bidirectional. So this is your equivalence relation. Uh, the moment you make it bidirectional, just look at this edge. The moment you make this as bidirectional, wherever the outgoing edge from 5, wherever the outgoing edge from 5 to any other node is, you must have an outgoing edge from 2 also, right? For transitivity. We will take another examples of equivalence relation. So just look at this for a moment. That again, what happens? You have two different components. Just like in the partial order, you have two. You had two components when it was partial order. In when it is equivalence relation, you see there are two connected components. The difference here is that in this connected component, whatever the nodes are involved, they all are related to one another. Every node is related to one another in a connected component. So in case of relation relation, every node or element involved in a connected component are related to one another. So in case of partial order relation, for every connected component, you will find an order among the elements. In equivalence relation, in every connected component, every element is related to one another. Let's take some other examples of equivalence relation. But because of this combination, reflexive, symmetric, and transitive, basically what I mean to say is that for a given equivalence relation, for any two elements which are related to each other, basically they are same on some attribute. They are equivalent. You call them equivalent. So 5 is equivalent to 2. In an equivalence relation, any two elements that are related to each other, we say that they are actually same or equivalent. And the relation, you define a relation on a given set with respect to that which two elements are same or with respect to some attribute. For example, let's say you have a set of your family members or extended family members. Now, let's say you have a set of extended family members. Let's say you have F is your family members, Gulam. One of the person is Gulam, another one is Moinuddin, and then Ramish is another person. Let's say A, B, C, all of these are extended family members, D and E. Now, with respect to every element, with respect to every person, like for example Gulam, then Gulam is of the same age as Gulam. So this is definitely, it is going to be reflexive. So whenever you have a condition on your relation that one element is related to another based on whether they are equal or same on something, with respect to something, then the relation that turned out to be that it will be a equivalence relation, because every element will be with respect to the same attribute, every element will be related to itself. And if two elements are related to itself, if two elements are related to one another, when they are same on something, then it goes both ways. And if Gulam is of age 28 and Moinuddin is of age 28, and let's say, and so Ghulam and Monuddin will be connected by a bidirectional graph. by bidirectional age. And if Ramesh, Moinuddin and Ramesh are also connected, what does it mean? It means Ramesh age is also 28, and so Gulam and Ramesh automatically would get connected. So they are transitive also. Let's say that A, B, and C, their age is 30, and D and E age is 42. Let's say Gulam is 28, Moinuddin is 28, Ramesh is 28. A is 30, B is 30, and C is 30, and D is 42, and E is 42. These are their ages. So A, B, and C, they are connected. A is related to itself because A is for 30 years old and A is 30 years old. Similarly, B is related to itself, C is related to itself. There is this bidirectional age between A and B, bidirectional age between B and C, bidirectional age between A and C. And when it comes to D and E, both are 42 years old. D is related to itself, E is related to itself, and there is a bidirectional age from D to E. So this is your, when you get this type of graph where every edge is bidirectional, and for each connected component, every node is related to one another. For each connected component, each element is related to one another. For this connected component, D is related to E is related to D. B is related to A and C is related to B and A is related to B and C. Similarly, Gulam, Moinuddin, and Ramesh, they are related to each other because all of them are 28 years old. So you can say that when you define an equivalence relation on on a set, so this is your set F. When you define an equivalence relation on set F, now what happens is that you are the elements of the set, you are basically, there's a partition being made in the elements of set, such that for every in every partition they are equivalent to one another. Okay, so the partitions made for F is, what are the partitions made on F because of the relation R? This is your relation R. So what are the partitions? How 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 relation R divides F into different partitions? Gulam, Moinuddin, Ramesh. This is one partition. A, B, C is another partition. D and E is another partition. So every element for a equivalence relation, for a equivalence relation, every element of F got to be part of any one partition, right? And Moinuddin, let's say for example, Moinuddin, it's a part of this partition. Then it cannot be part of any other partition. Because if Moinuddin age is 28, it cannot be related to B because this partition means the elements whose age is 30. This partition means the elements whose age is 42. This partition means those elements whose ages is 28. So no any element of F can be in more than one partition, and they have to be in one of the partition. Yeah, that's it. Let's take one another example of equivalence relation and we will end this video. So, so when I am trying to give one more example, how should I think? Means I may think that okay, I will take set of something and I will relate them based on who has the same value for a given attribute. For example, let's say I take a case of men and women, a set of men and women, and I might say that, okay, two elements are related to one another if they have the same gender. Means same gender people are related to one another. Let's take an example. So look at this. This is your set, set of some people. Some of them are men and some of them are women. And we are going to apply a relationship on S based on means a relation X is related to Y if X and Y are of the same gender. So every element is related to itself because Gotham is man and Gotham is man. So Gotham is related to Gotham. So Gotham is related to Gotham. Musk is related to Musk. Okay. Now, all of the men are related to one another. So this is going to be like this. So every one of them are related to one another. So it is going to be something like this, right? Similarly, Hema, Rekha, Jaya, Shushma, all of them are women. So this is your equivalence relation. This is your relation on S, where this is equivalence relation. So what are the partitions on S because of this equivalence relation? What are the partitions on S because of the relation R? One partition is Gautam, Musk, Narendra, and Donald, Hema, Rekha, Jaya, Shushma. Okay, that's it for this video. We'll see more on the next video. Thank you very much.